Jai Hind everyone. My name is Abhishek Gupta. I am working as an assistant professor in Ajay Kumar Garg Engineering College. Today, I will cover one of the complex topic of a material science subject, which is based on the mechanical properties of the material. So, in our today's discussion, we will discuss the stress strain curve, the tensile test, and the plastic deformation and its mechanism, dislocation strengthening, grain size reduction, solid solution strengthening, and strain hardening. These are basically the strengthening mechanism which we will discuss today. Then creep, hardness, different types of hardness, what is Griffith criteria, fatigue failure, and SN curve. All these topics we will discuss today. So, firstly, any material is subjected to various different types of loads, and due to the different types of loads subjected onto a particular material, various types of deformation has been seen onto a particular material. So you can see that this is the cylinder in which a tensile force F is acting, and its initial cross section area is A0, but after the tensile force F is working, its cross section area has been changed, and when the compressive force is acting, then we can see then also the cross section area and length has been changed. On applying tensile forces, length is increasing and area is decreasing, whereas on applying compressive forces, we can see the area is increasing, cross sectional area is increasing, but the length is decreasing from L0 to L. Similarly, here shear forces has been applied. Due to the shear forces applying onto a particular cube or to a particular spherical surface, we can see that angular distortion has been seen on these two materials. So from the perspective of loading, stress is the induced force or the system of forces that tends to deform the body. So the stress definition can be defined as the maximum value of internal resisting force that a body can sustain per unit area. Then that per internal resisting force per unit area is defined as the stress. Based upon stress, there always has been associated with the strain, and strain is actually the response of a system to an applied stress. Whenever a material is loaded with a force, it produces stress, and then it causes a material to deform. So this deformation things can be studied in the strain. So coming on to the strain, engineering strain is defined as the amount of deformation in the direction of applied force divided by the initial length of the material. So if the amount of deformation will be more, then strain will be more. If the amount of deformation is less, then strain will be less. This is the standard tensile test specimen with a circular cross section. So you can see that this is the I section, and this area is the grip section. This is the width of the grip section. This is the overall length of the I section. This is the distance between the shoulder. This is the gauge length. This is the diameter and the width. And this is the reduced section. So the whenever you have to perform tensile test on a particular specimen, then the tensile test performed on that universal testing machine. For that, we have to prepare the specimen. The specimen size, shape and size actually corresponds to this one. So this is the standard tensile testing machine, which is the universal testing machine. And here the extensometer has been attached to this I section, which is known as a specimen, on which a particular tensile force has to be applied. So this is the moving crosshead, which is going downwards. When this moving crosshead is going downward, due to the downward motion of the moving crosshead, this extensometer shows the reading based upon what type of elongation this specimen faces during performing particular tensile test on this universal testing machine. So this is the relationship between stress and force, internal resisting force, sigma is equal to F by A naught, and its unit is megapascal. And we know 1 megapascal is equal to 10 to the power 6 Newton per meter square. Here force unit is Newton and area unit is mm square or meter square. This force unit is also measured in pounds per square inch, which is PSI. This is customary unit USA. Coming on to the engineering strain. Engineering strain is defined as the change in length upon original length. So since in numerator also length is there and in denominator also length is there, so it is unitless quantity. When you multiply with the 100, you will get the strain in percentage. So this is the actual stress strain curve drawn for actual stress strain curve and the engineering stress strain curve. Here you can see this is the diagram which has been formed for the stress strain curve. This is the proportional limit. After that, elastic limit is there. Then yield point is there, upper yield point, lower yield point. Then after that, ultimate tensile strength is there. And on increasing more forces, we can see that the strain is also increasing. This dot line shows the actual rupture strength at this point. This is the true stress strain curve, and this is the engineering stress strain curve. At this point, the material ruptures, and the strength at this point indicates the rupture strength. So this diagram is actually drawn for ductile material, which actually shows each and every deformation phases for a particular material like ductile material. We can see through the stress strain graph. So the stress level at which the plastic deformation begins is known as yielding stress, and the proportional limit is the limit which actually denotes the highest stress in a stress strain curve, and this proportional limit is actually indicated by the straight line. Up to the proportional limit, we actually see no permanent deformation, but beyond that, if this proportional limit has been crossed, then the object does not return to its initial position. Then at that time, we can say that the plastic deformation has been occurred into a particular material. So every material has some tensile strength, and this tensile strength is actually the stress. At a maximum value of engineering stress strain curve diagram, we can actually find out the tensile stress. And this tensile stress corresponds to the maximum stress that a particular structure sustains when a tensile force is applied to it. So if this stress is applied and maintained, then obviously fracture will result. So this is now we will discuss various different types of mechanical properties. Like first is the ductility. Ductility is an important mechanical property which actually measures the degree of plastic deformation up to the fracture limit. So a metal, if it experiences very little deformation or no plastic deformation upon fracture, then that type of material is known as brittle material. And if there is shown significant deformation when a particular force is applied onto a particular material before its fracture, then that material comes under the category of ductile material. In case of ductile material, we see each and every points, that is upper yield point, lower yield point, proportionality limit, elastic limit, rupture strength. Resilience is the capacity of the material to absorb the energy when it is deformed elastically, and then upon unloading to have this energy recovered. So resilience is actually represents the capacity of energy absorption when it is actually elastically deformed, and when we unload the forces from a particular material, then this energy is again restored. Then toughness is that property of indicative of the material which actually shows the resistance to the fracture when a crack is present. And because it is nearly impossible to manufacture any material with zero defects, that's why every material has a certain amount of defects during its manufacturing. So toughness actually indicates the material resistance before fracture, that is when the crack is actually present inside the material and that crack propagates. So hardness, next coming on to the hardness. Hardness is the measure of material resistance to the localized plastic deformation. That is, whenever there is a small dent or scratch, then this localized plastic deformation, which we actually see during performing the hardness test, it actually denotes the material ability to withstand friction or to withstand abrasion. So this property, which the material which resists the plastic deformation, uh, this property is known as hardness. Coming on to the next topic is the elastic deformation. Elastic deformation is the temporary shape change that is self-reversing after the force is removed, so that the object returns to its original position. Then this is known as elastic deformation. If the elastic deformation is crossed, then the material reaches in the plastic deformation. So if we remove the forces before elastic deformation stage has been reached, then the material recovers its initial position after the external force has been removed. So no change in shape is seen upon load removal into a particular material during elastic deformation. Then second term is the plastic deformation. Plastic deformation is the permanent distortion that occurs when a material is subjected to tensile, compressive, bending, or torsion stresses. That when the material exceeds its yield strength, and causes the material to elongate, compress, buckle, bend, or twist. So different types of distortion has been seen when the material exceeds the elastic limit and comes into the plastic deformation zone. Then the zone which actually shows the deformation, permanent deformation, then this permanent deformation is known as the plastic deformation, and there is always seen the change in the shape of the particular material upon removal of the loads. So actually there are two different types of plastic deformation mechanism. One is the slip mechanism and another is the tuning mechanism. Then coming on next to the strengthening mechanism. Strengthening mechanism shows the relationship between the dislocation motion and the mechanical behavior of the metals. Actually, this dislocation is also known as the line effect. Whenever the group of atoms are present into a particular material, this group of atoms shows some systematic distribution of distribution into a particular material, and whenever this systematic distribution has been disturbed when a particular force is applied or a particular treatment has been done to a particular material, then this dislocation moves from one point to another point. Due to this movement of one point to another point of the atoms into a particular material, various different strengthening mechanism has been created, which actually increases the strength of that material from lower strength to the higher strength, and that's why the behavior of that material changes in a very drastic manner. So the ability of the material to plastically deform depends upon the ability of the dislocation to move, and the restriction or hindering this dislocation motion renders a material harder and softer, harder and stronger. So if this dislocation is removed, is hindered, then we will see that the strengthening property or the hardness property of that material is going to increase. So you can see this is the strengthening mechanism. Strengthening by there are three different methods for strengthening. First is the grain size refinement. So you can see that the different atoms are present into a particular orderly manner, and you can see that these are the atoms which are present in the same material. So you can see that the arrangement of these atoms and these atoms are entirely different, and these arrangement of atoms shows some certain grain boundaries. So these grain boundaries actually separates the atom into different locations into a particular material, and you can see also that here, but in horizontal direction also and in vertical direction, the arrangement of atoms are also different. So if you will decrease the size of the grain, then the grain boundaries will increase, and this grain boundary increases causes the strength to increase into a particular material. So by reducing the grain size of a particular material, or dislocation motion causes the strengthening of that particular material when we decrease the grain size. So you can see the stress strain curve here shows the work hardening, which is also known as strain hardening. This is the second method for hardening a particular material. So you can see that how stress and strain curve actually varies and then again it reaches to B, and again this stress strain curve reach to the point S1 and then D1 point. So whenever you apply some external force onto a particular material, then that external force causes the material to become hard, and due to this work which we actually perform onto a particular material causes the strengthening of that particular material, and due to this property the strength property actually increases in that material. So then third is the strengthening by solid solution. So solid solution are basically of two types, that is substitutional solid solution and interstitial solid solution. We have already discussed in the previous lectures. For example, in case of copper in nickel shows the substitutional solid solution, and carbon in iron shows the interstitial solid solution. Whenever external element adds up into the base material, it always uh, uh, causes the force onto a different material, and this different material produces equal and opposite force to the previous metal element which has been added to the in order to form the alloy, and this process causes the solid solution to get strengthened. So with the help of this solid solution strengthening mechanism, a particular material can increase their hardness or strength based upon the other substitutional solid solution mechanism has been occurred, or interstitial solid solution mechanism has been occurred. Then this is the strengthening by solid solution. You can say that this bigger atoms takes the position of the smaller atoms, and due to this bigger atoms taking the position of the smaller atoms at the substitutional sites, you can see that how the stress has been created inside the material. So due to the stresses inside the material which has been created, this stresses uh, enforces the other material to dislocate from its initial position. So whenever a dislocation has been seen onto a particular materials, it increases the hardness, which we have already discussed. So next mechanism is the creep mechanism. So this creep is a time dependent process where a material undergoes an applied stress, exhibits a dimensional change at high temperature. So this creep phenomena actually is the temperature dependent phenomena, and this high temperature progressive deformation is known as the creep. Creep always increases with temperature. If the temperature is more, then the creep will be more. Creep phenomenon is also known as time dependent phenomenon because as the time progresses, we see that there is some deformation into a material whenever a constant load has been applied, and this constant load at high temperature causes the material to deform, and this deformation which we actually see at constant temperature and at constant high temperature and at constant load causes the deformation, and this phenomenon is known as creep. Normally creep occurs when the vacancies in the material migrate towards the grain boundaries that are oriented normal to the direction of the applied stress. So whenever there is the vacancy or the point defect into a particular material, and when we apply the load, due to the application of the load, this vacancy starts to move from inner space to the outer space, especially in the direction of applied load. Then this causes the material to deform, and this mechanism is known as creep. Creep temperature is generally considered to be 40% of the melting point. This is an important point which you have to be noted. So this is the diagram for creep, strain, and the time. So you can see initially there are three different types of creep: primary zone, secondary zone, and the tertiary zone. You can see that with the increase in the temperature, creep is increasing in a very fast manner, and then in secondary zone, as the time is increasing, the creep strain is also increasing in a linear manner, and in the tertiary zone you can see with the increase in time, this creep strain is increasing in a very slow manner. So you can see that this and at this point actually rupture happens for a particular material. So this graph has been drawn for a particular temperature and for a particular stress. By applying particular load onto a particular material and keeping that material for a longer duration of time, we actually see the deformation, which is known as the creep strain. So this is the actually the creep testing machine. Here usually the tensile bar has been kept and actually a dead load has been applied, which is of constant magnitude, and the strain is plotted versus time, which we have seen before diagram. And this test usually ends with rupture. So you can see that a furnace is there which actually maintains the temperature, that is 40% of the melting point, and a constant load has been applied, and this due to this constant load applied into a particular temperature at constant temperature causes the material to fail, and the material at which deforms at constant load shows the strain, and this strain versus time curve has been drawn in case of the creep testing. So this is the graph for the creep strain and the time at different temperature. This is the T1 temperature, T2 temperature, and T3 temperature, sigma 1, sigma 2, and sigma 3. This T1 is the least temperature and sigma 1 is the least stress. This is the intermediate temperature and the intermediate stress. This is the higher temperature and the higher stress. So you can see as we go on increasing the stress or the temperature, instantaneous strain is increasing. Here strain is less, here strain is more, and here strain is most. And we can see that there is always with increase in the stress or temperature, steady state creep rate increases. Creep rate is also increasing. You can see. Also the time to rupture decreases. Initially this rupture has been, we have found with at this time. Here time decreases and here time also decreases. Then next topic is the hardness. Hardness are performed more frequently than any other mechanical test, and this has been performed because of the various reasons. First reason is that this is a simple and inexpensive process. Ordinarily, no special specimen need preparations, and the testing apparatus is relatively inexpensive. So this test is actually the non-destructive test, and this specimen is neither fractured nor excessively deformed in order to get the hardness value of a particular material. Here only a small indentation has been formed onto a particular materials on which you have to perform the test. Other mechanical properties often may be estimated from hardness data such as the tensile strength. So you can see this is the hardness test, Rockwell hardness test. The hardness number is determined by the difference in the depth of the penetration resulting from the application of an initial minor load followed by a larger major load. You can see the firstly minor load has been applied. This is a zero reference. Then some minor load has been applied. Then some major load has been applied. So you can see that this is the indentation which we actually see inside the specimen, and this indentation helps us to determine the Rockwell hardness value for a particular specimen. So this is the machine for Rockwell hardness test. So this Rockwell hardness test indicators includes the spherical and hardened steel balls having diameter of around 1.588, 3.175, 6.35, 12.70 mm. And there is one conical diameter, that is Brill indentator, which is used for getting the hardness of a particular material. And this hardness test is basically preferred for non-ferrous and light alloys. Then second hardness method is the Brinell hardness test. In Brinell hardness test is same as like the Rockwell hardness test. Here a hard spherical indentator is forged onto the particular surface on which the testing has to be performed, and the diameter of the hardened steel, that is which is made of the tungsten carbide, which is also known as the indentator, is around 10 mm. And the standard load ranges from 500 to 3000 kg in 500 kg increment and value during the test. So this load is maintained for a constant duration period of time, that is it ranges from 10 seconds to the 30 seconds. Then another test is the Knoop test and the Wicker hardness test. And this Knoop test and the Wicker hardness test, this Wicker test is also known as the diamond pyramid test. And in these both tests, a very small diamond indenter is pyramidically shaped diamond indenter is forged onto the particular specimen, and we apply much smaller load in comparison to the Rockwell and Brinell test, and this load actually range from 1 gram to 1000 gram, and the resulting impression is observed under a microscope and measured. this impression which we actually get when we indent the diamond indenter onto a particular specimen. This cross section diagonal is measured, and this diagonal measured, when we put that into a particular formula, it gives the hardness value for a particular material. So careful specimen surface preparation like grinding, polishing is necessary before performing these tests, because if we will not do polishing and grinding, then it will not be possible for us to see the diagonals, measure the diagonals, or see the indentation onto a particular specimen. Then it's a it's measuring hardness value is not possible. So proper grinding and polishing is necessary before coming on for this test. So these are some of the formulas for Brinell hardness test, Weaker hardness test, Snoop hardness test, Rockwell hardness test. So you can see this here. P is the load, capital D is the diameter of the ball, and small d is the diameter of the indentation. So with the help of these, we can actually measure the Brinell hardness test. Similarly, here L is the length of the diagonal. Here also length of the diagonal. So Rockwell hardness test is divided into A, B, and C, D, E, F. Different Rockwell parameters are there. Based upon that, we have defined the Rockwell hardness test in various categories. So we can see that every atom has some atomic arrangements, and always there is a spacing between the two atoms. And whenever a force is applied onto a particular material, this spacing firstly increases, you can say, and some energy is getting stored into that. And when we increase the displacement after when maximum force has been reached, then we can see that displacement between the two atoms increases, but the force gradually decreases. So you can see from this curve. So next point is the Griffith criteria. Griffith criteria is actually the criteria which is given by Griffith, which actually describes the relationship between the applied normal stress and the crack length at the fracture. Suppose this is the crack length which was originally present inside the material, and if we applied some stress, that is sigma, onto a particular material before perpendicular to this cross section, so we can see that this crack is going to propagate. And when this crack is going to be propagate, then we can see that this crack will cause the material to fail. So Griffith criteria is concerned with the energetics of the fractures and consider the energy changes associated with incremental crack extension. So here F actually denotes the failure and sigma actually denotes the stress. So the failure stress is actually shows that it increases with the square root of the bond energy, where E represents the bond energy, and this finally the quantity is combined into the Griffith critical energy release rate, which is represented by the Gc. Here A is the crack length. Then next topic is the fatigue. Fatigue is a form of failure that occurs into a structure when a dynamic or fluctuating stresses has been applied to a particular material. This dynamic loading which we apply to a particular material, this is in cyclic nature. Fatigue failure actually we see there, and this failure we see like bridges, aircraft, machine components which are continuously in a running conditions. So under these circumstances, it is possible for failure to occur at a stress level considerably lower than the tensile or yield strength for a static load. So the term fatigue is used because this type of failure normally occurs after a lengthy period of repeated stresses or the strain cycle. So whenever a material is subjected for a longer duration of time for particular type of stresses, then it may be happen that the material actually fails before the yield point. So the point at which that material fails below the yield point is known as the endurance limit for a particular material. So you can say that this is the stress and time curve, and stress is varying. Above point shows tension and below point shows compression, and this is the stress and time curve. Here stress and how stress and strain curve is varying. So the fatigue is actually the process of fatigue failure. There are three different stages. First is the crack initiation, then crack propagation, and the final failure. So crack associated with fatigue failure almost initiates or nucleates at the surface of the components where higher stress concentration region is there, and this crack propagates starts from the surface scratches, sharp fillets, or keyways or thread ends. In addition, the cyclic loading can produce microscopic surface discontinuities resulting from dislocation slip steps that may also act as a stress razor and therefore as the crack initiation sites. So you can see this is the fatigue. Whenever a load is there, you can see initial there is some crack. When a load is applied, this crack combines, then this crack propagates, and final fracture we see. So this is the rotating beam fatigue testing machine on which the fatigue test has been performed. And you can see this is the specimen which has been kept between the head and tail stalk. And here one extensometer has been used, which actually senses how much elongation has been occurred onto a particular materials. And here the motor actually causes the cyclic loading onto a particular materials. And this test has been performed onto a particular material for more than 1.5 or 2 days. Then only we can actually find out the fatigue load or fatigue failure we can see onto a particular material. So you can see that the failure has been seen here. So this fatigue failure, with the help, in order to understand the fatigue failure, we have to draw the SN curve, and this SN curve actually shows the is drawn between the stress and the number of cycles before fracture. Here x-axis is the logarithmic scale and y-axis is the actually denotes the stress. So you can see that here fatigue strength is there at N1 cycle, and here number of cycles. So as we go on increasing the number of cycles, the strength is decreasing. So when the number of cycles is more, the strength will be less, and this strength actually shows the fatigue strength, and this fatigue strength is also known as endurance limit. And this endurance limit is very less, approximately 3.4 to 0.3 times of the yield point failure. So what are the factors which actually affect the fatigue life? For more common loading situations, the maximum stress within a component or the structure occurs at the surface. Consequently, most cracks leading to fatigue failure originate at the surface where stress concentration is high, and it has been observed that this fatigue life is especially sensitive to the configuration and the condition on which the component has been subjected. So there are various factors like design factor is there, which actually causes the sharp discontinuity, causes the material to sudden fail. Surface treatment we have to perform, like case hardening has to be done in order to avoid fatigue failure. In case hardening, carbon or nitrogen induces into a particular material, and due to this diffusion in gaseous phases increases the hardness property of that material. Thank you, class. This was my lecture. If you need any clarification regarding this lecture, you can mail me at Gupta Abhishek 34 at the rate Gupta Abhishek at the rate akgec.ac.in.